Hey guys, so there's no recitation this week, but I am going to go over last spring 2017's final exam, which is on the website, just as some review. If you find yourself going over that to study and you have questions, you can look at. I'll try and go over kind of why we answer the way we answer for all of these. As always, feel free to email me with questions, but keep in mind I won't be able to answer questions during the time that the final exam is open, so email me all of those. I guess today would be good, or tomorrow morning. Okay, number 1, the 3 isomers of pentane, C5H12. Their structures and boiling points are shown below. Use the molecular structures to explain why the boiling point is the lowest among the 3 isomers. So which one is, so this one is the lowest boiling point. And so we see pentane it's all spread out. Let's draw 1, 2, 3, 4, 5. And then we have butane that's also, butane is also, it's a little more spread out, but pentane is super spread out, right? It's almost a ball. So it looks like pentane, you can make there are a lot of van der Waals forces, a lot of those dispersion forces, what we call them. And so as the molecule gets more bunched up, there are fewer of those dispersion forces. So let's see what mentions dispersion forces. So there's dispersion forces in C. The pentane and 2-methylbutylene have longer chains, which have larger dispersion forces. And so that's our answer. Which of the following molecules would be expected to form hydrogen bonds? Remember, a hydrogen bond is HO, HF, and HN, I believe. So, and it has to be hydrogen bonded to one of those elements. So we have an OH here and an OH here. Now, could we make a hydrogen bond between this an H and an O? That doesn't work. So we'll say ethylene glycol and methanol. Number D. In order for water to boil, what intermolecular forces between water molecules must be overcome? Well, a water molecule has hydrogen and oxygen. Okay, and water molecules, since you have those O's connected to those H's, you can make hydrogen bonds there, which is the most specific. That's a type of dipole-dipole, right? So you have hydrogen bonding and dipole-dipole. Everything has dispersion forces, right? And then you have this ion dipole here. And an ion dipole, do we have any ions in water? We don't, right? An ion is when basically they're no longer sharing electrons. There are 2 charged ions that are attracted to each other. And since we don't have any ions in water, we'll go with C. Consider the phase change shown in the picture. The phase change occurs at constant temperature even though heat is being removed from the system. Where would this phase change occur on the cooling curve? Okay, so this is basically saying, so we have like our gas here, and then we go to, this is where it starts becoming that phase change from gas to liquid, and then it's all liquid, and it becomes solid, and this is solid to, you have and liquid to solid transition, sorry. So this is the liquid cooling down and then becoming a solid, and here it's a solid and cooling down, right? So we are curious at, we are curious about the phase change. Okay, so we're asking what is this phase change? So it looks like it's initially a solid. That looks like solid, right? They're all tightly, well, is that solid? This is a gas phase, right? So this must not be solid. This must be a liquid phase, right? Because we don't really, in this temperature diagram, we're not going from liquid to solid. We're going to gas to liquid, right? We don't, gas to solid is like sublimation or whatever, and we're not, in the temperature diagrams, that doesn't happen, I guess. So we're going from a gas to a liquid. So where would the phase change occur? Gas to liquid, we decided, was B to C. So we'll go with B. Which of the following phase transitions is endothermic? Gas to solid, liquid to gas, liquid to solid, or gas to liquid. So an endothermic reaction means it's absorbing energy, right? Whereas an exothermic is when it's releasing energy. So that means heat is being added. So we're doing the opposite of this temperature curve we just saw. So we're adding energy to make it we're adding energy to change the phase. So if we go from gas to solid, that goes this way. That's reducing energy. Liquid to gas, that goes this way. So that works. Let's check. Liquid to solid again goes this way, and gas to liquid again goes this way. So this is the only one that goes the opposite direction. So even if you didn't know what endothermic meant, you could still kind of figure out, well, they're all going in the downhill direction, except for this one is going uphill, or even they're all going, yeah. So kind of, you can always use the process of elimination if you don't know something. Which of the following best represents the balanced equation for dissolving Na3PO4 in water? So Na3, how are we going to, okay, so we know it's divided into Na and PO4 minus, PO4 3 minus. That's just kind of based on everything they give us, except for this one, solid to liquid. We know it doesn't turn into liquid when it dissolves. It turns into an aqueous solution, so we can ignore D. So we have sorry, I'm gonna add the plus there. So let's figure out what the difference is. Okay. Oh, so this is a trick. Is this gonna be a 3? Ooh, I'm not sure what happened there. So is this going to be a 3 minus or just a minus? It looks like it's one thing we want to consider. And is this going to be a 1 or a 3? Well, we can see since this is Na3, that means we're going to have 3 Na pluses. So we can eliminate this one, because Na3, those are all going to separate. They're not going, and even if they didn't separate, it would be Na3 3 plus is how you would write that, because each of those Nas has a positive charge of 1, I guess. So that's not, but each of those each of those sodiums is going to separate. So we can ignore that first one. And then PO4, well, if it just had a -1 charge, then we would need only 1 sodium, right? Because Na, we know, has a charge of +1. So that means that PO4 3 is going to have a charge of -3. So that's why we have the 3 sodiums to balance it out. So we're going to go with C on that one. The Lewis structure for methanol, which following images shows how they would hydrogen bond. Okay, so the first one, we have this oxygen, and it's hydrogen bonding with this hydrogen. Now this hydrogen is attached to a carbon. And remember, when the hydrogen is attached, the hydrogen has to be attached to an oxygen, a fluorine, or a nitrogen to be able for a hydrogen bond to form. So if it's attached to the carbon, that's not a hydrogen bond. Now here we have the same thing happening again, right? The hydrogen is attached to a carbon, so that's not going to work either. Which leaves us with C, and we see our hydrogens and our oxygens are attached, and the hydrogens that's forming the hydrogen bond is attached to an oxygen in both cases. So that works. So our answer is C. Okay. Based on the idea that like dissolves like, what type of solvent is expected to dissolve a molecule that is polar? So, like dissolves like, so the answer is A. If you think about replace like dissolves like with the same word each time, so polar dissolves polar. You can't say polar dissolves nonpolar. That's not what this form of the phrase is saying, I guess. So basically the idea is that polar solvents dissolve in each other. So if you mix water with alcohol, those are soluble, whereas if you try to mix oil and water, oil is nonpolar while water is polar, so those do not dissolve into each other. What is the total concentration of ions present in the 0.15 molar aluminum sulfate, Al2SO4 3 minus, SO4 2 minus? So it looks like we have Al, because we have two of those, and I'm not sure what their charges are. Well, they're going to be 3 plus, right? Because we can use kind of those crisscross rules. And then we have SO4 2 minus, and we have 3 of those. Basically, if you multiply 3, sorry, it's going to be 2 and 3, isn't it? Basically, you want, when you multiply 3 times its charge is going to be, no, it is 2, I was right. Sorry. So when you multiply it by the charge, 3 times 2 is negative 6, and 2 times 3 is positive 6, so those will cancel out. You'll get 0. So basically, we have 1, 2, 3, 4, 5 ions for every 1 molar of aluminum sulfate, but we only have 0.15 molar, so we'll do 0.15 times 5, and that is equal to 0.75, I believe. In class, we talked about surfactants and their applications in respiratory distress syndrome in infants and in agriculture. For example, the leaf with water on it. Okay, how does the presence of a surfactant molecule change the ability of the water to wet the leaf? So the surfactant, remember what a surfactant does, is it has some polar end and some nonpolar end. And so the polar end can mix with stuff like water, whereas the nonpolar end will mix with like the waxy cuticle on the leaf. So let's see what, if anything, talks about the IMFs, right? Because this is kind of the intermolecular forces, the polar and nonpolar. So it lowers the molecular weight, so that doesn't really have anything to do with IMFs. Change the boiling point of the solution. Well, that has, let's leave that one for now. Acts as a buffer in the solution. That doesn't have anything to do with IMF. And interacts with the molecules and lowers the surface tension. Well, surface tension is also an IMF. So we have boiling, which doesn't really happen on leaves, right? And the surface tension, now that kind of makes sense because basically when the surface tension is lower, the water is able to spread out. So we'll go with D for that one. What impact does a catalyst? Oh, I'm going to go over this in the next video.